Hello, everybody. Welcome back to Monte Carlo Methods. When we last left off, we were talking about random number generators, and as promised, I am not doing that justice at all and dropping that subject abruptly now to get into what I think is the real start of the course, because the point of the course that I'm trying to bring to you is what we can do with those random numbers. We can make a lot of magic happen, and we will. Now, in today's video, I'd like to test our random number generator, and if that sounds like something you're not interested in, the test we're going to be doing, so you might think, let's jump to the magic, let's start generating other things. The things we're going to be doing in this test can be used for other things you might simulate and want to test. Specifically, our test today is going to work whenever you simulate values from any univariate continuous distribution for which you can write down a CDF. So for example, suppose you want to simulate values from an exponential distribution with rate lambda. Here is the PDF. It is lambda e to the minus lambda x for x greater than 0. And if you knew how to simulate values for this distribution, and we don't know how to do that yet, then you would make a histogram at this point and use the proper scaling like we talked about and density on the y-axis, and hopefully get a kind of match for this PDF. Now, this looks close enough. That is the question. It passes my eyeball test for exponential random variable simulation, but can we do a more formal test? And if we develop a more formal test that works for any univariate continuous random variable, we can also apply that test to testing for draws from a uniform distribution. In other words, for testing our random number generator. PDFs, or probability density functions, are notoriously hard to work with in situations like this because they don't represent probability on their own. When you evaluate a PDF at a point, that's not giving you a probability. Instead, as you know, it's a curve under which area represents probability. And matching it to a histogram that we create from our data is also maybe problematic because your histogram can look different depending on how you scale things and the bin width you choose. So maybe I can have the exact same data and make a histogram that fits a little nicer if I tweak it a little bit. So I wouldn't spend a lot of time trying to match the PDF to a histogram. Instead, we're going to move to the CDF, or cumulative distribution function, for the underlying distribution. A CDF is usually denoted by a capital F of x, and it's defined to be the probability that x is less than or equal to x, where x is a random variable with the distribution of interest. Again, rather than trying to match our histogram to a probability density function, we're going to move everything into the cumulative distribution function space, if you will. So you know how to get a CDF from a PDF. You just need to integrate from, in general, minus infinity up to x. For the exponential distribution, it's enough to start your integral at 0 because there's no probability down here from minus infinity to 0. But in any case, you know how to get a cumulative distribution function. And for this video, I mostly want to talk about how to get a sample version of the cumulative distribution function. The sample version is known as the empirical CDF, or usually and more commonly actually, the empirical distribution function. The word empirical implies that this is something we're observing, like we're observing from the data or the sampled or simulated values, and we're going to try to build a CDF out of that to match to the true theoretical CDF for our target distribution, or target, the thing we're trying to sample from. In my picture, it was exponential. If you're testing a random number generator, it might be the CDF for a uniform distribution. So let's get right into it. The empirical CDF, how are we going to come up with one based on data? As an example, I'm going to suppose that we have generated or simulated 4 values from a distribution for a random variable x. Suppose I get these numbers right here. I just want to note at this point that these numbers are rounded just to make nice-looking slides. If you're truly trying to simulate values from a continuous distribution, you probably don't want to round off your numbers like this. It almost looks like a discrete distribution. And in fact, if you're limiting yourself to only going out to 2 decimal places, then you can enumerate all of those values and treat it as a discrete distribution. So these are supposed to be values from a continuous distribution. And when I work with them and actually do the test that we're headed towards developing today, I want to use all the digits that I have. But again, for the slides, I rounded these off. These are supposed to represent copies of the random variable x. So usually we would call these before they're generated, because once they're generated, they're numbers and not random variables. But before they're generated, if I'm going to generate 4 values and don't know what they're going to be, and they're still random, I'm going to call those values capital X1, capital X2, capital X3, and capital X4, a random sample, if you will. These values are realizations or observations of that random sample. Now, I'm assuming the underlying distribution, this random variable x here, has a CDF that we're going to call capital F of x, and that would be the same CDF that would be attached to each and every one of these copies of x because they all are identically distributed. Let's talk about estimating a CDF from data, and then once we can do that, we can talk about how close our estimated CDF is to the true CDF of the target distribution, the thing we're trying to simulate values from. Let's look at this list. If you like, you can order these values. That might be helpful at this point. I'm not bothering because there's only 4 to look at. But to pull a number out of the air, just looking at these 4 values, these are supposed to be observations for x. So what do you think the probability of seeing an x less than or equal to, say, 4.11 is? Based on these values, they're all less than 4.11. So based on these values only, I'm going to guess, my best guess is that the probability that x is less than or equal to 4.11 is 1. This is kind of how we're going to build our empirical CDF, which I'm going to denote with a capital F hat of x. And so what I'm saying here is that capital F hat of 4.11 is 1 based on this sample alone. I'm sure you might think, well, if I generated more values, I might see values above 4.11, but that's not what we're doing. We're taking the sample and using the information in the sample only to build an empirical distribution function. So just to pull one more number out of the air, suppose I want to evaluate or define my empirical CDF at the number 2.38. So based on this sample and this sample alone, what do you think the estimated probability that x is less than or equal to 2.38 is? If you look at these numbers, 3 out of 4 of them fall into that condition of being less than or equal to 2.38. So I would estimate that the probability of seeing an x less than or equal to 2.38 is 3 out of 4 or 3/4. So we can keep picking out individual numbers to evaluate an empirical distribution function, but let's try to do it all at once, at least graphically, and then we'll write it down as a nice tight formula. I have created some axes here. I've put my data on the x-axis, and now they are in order. And I want to define an empirical CDF, which is going to be what I'm plotting here, for all values of x. So bear with me for a moment and just look at a value, say, down here. Just suppose we pick the value 0.279. That's something less than our smallest value of 0.32. Based on the data, what do you think is the probability that x is less than or equal to 0.279? The answer is 0 because we don't see any values less than or equal to 0.279. And indeed, the empirical CDF is going to be defined to be 0 for all x values below this 0.32, where we actually start observing values in our data. Now, when we get to that value 0.32, the empirical CDF, or estimated probability that x is less than or equal to 3.2, based on looking at these 4 data values, appears to be 1 out of 4. So the empirical CDF is going to jump to the height of 1/4 right here when x is 0.32. To grab another value, a little bit above 0.32, but not as high as 0.47. So if we look at, say, 0.4, what do you estimate is the probability that x is less than or equal to 0.4? Looking at these data, there's 1 out of 4 that is less than or equal to 0.4. So the estimated CDF should still be 1/4 all along here until we actually hit the x value of 0.47. At that point, you say, what is the probability that x is less than or equal to 0.47? Based on these data, it appears to be 2 out of 4, or 1/2, because there are 2 numbers here less than or equal to 0.47. So the CDF is going to jump up by another distance of 1/4 to a total height of 1/2. Continuing in this way, we get a full step function with 4 steps. We have equal jump heights. They're all jump height of 1/4. And any CDF should be 0 in the limit as you go off to negative infinity and 1 in the limit as you go off to positive infinity. And we're seeing that right here in our estimated empirical distribution function. This distribution function is based completely on this particular sample we simulated, or I simulated. I didn't tell you where I got these numbers from. In fact, I made them up for an example. But if you had an algorithm to simulate values from this underlying distribution for a random variable we were calling x, and you simulated 4 values, or even I did it again, I wouldn't get the same 4 values. In that case, the empirical CDF would look a little bit different. It would still have 4 steps like this. The jump heights would all be 1/4, assuming you are actually using all your digits. And, if you have a lot of digits and you're simulating from a supposed continuous distribution, you're not going to get any points in your data set repeated. And this means that all the jump heights would be 1/4 or 1/n in general if you had n data points. If not, if you actually have repeated values, you can work with that as well and have a jump height of 2/n or 3/n or whatever is appropriate based on what you're looking at. But again, with a new sample of size 4, you're going to see something a little bit different. And we are trying to figure out what you should see if you are truly simulating from a distribution with CDF F. Because if we know how this empirical CDF behaves when you are truly doing the right thing, then we can look at what we expect to see and how far off we could be from the original continuous underlying CDF. So my questions for you is, with an empirical distribution function, with still a random sample before you've observed things, what do you expect to see? And how much do you expect it to vary between sampled values? Each time you get a new sample of size 4, you're going to see a little bit of change and variability, and how much variability do we expect? Again, for each fixed real number little x, the capital F hat of x is a random variable before we have made our observations and drawn a graph like I had on the previous slide. And again, we want to learn about how this random variable acts so we know whether or not it's going to get close to the true f if we are doing the right thing in our simulation. We want to know how this random variable is going to behave, so let's take a closer look. First, I'd like to give you, as I said, a tighter definition here. So suppose in general we have a random sample, capital X1 through capital Xn, from any distribution with CDF capital F. I did say that we were talking about continuous random variables today, but actually for this empirical CDF discussion, they could be discrete as well. It's not important. It's the ultimate hypothesis test in the end of this video, which may even get pushed to the next video, about how close the empirical CDF is to the true CDF. That test will depend on us looking at a continuous distribution, but the empirical CDF can be defined the same way we're doing it here, even for a discrete distribution, so I won't put the word discrete in here. Again, the CDF capital F is the probability that any one of these xi is less than or equal to x. x1, x2 through xn, these are all like copies of x, or maybe there's no original x. You just say, I want to simulate from a distribution. You don't actually refer to, I want to simulate a random variable x from a distribution. We're just simulating n values from a distribution. The words random sample, you may know from another probability or statistics course, is equivalent to saying that they are independent and identically distributed, or we use the acronym IID. So if you see random sample, it's assumed that these values are independently produced. In order to give you a nice tight representation for the empirical CDF, I want to first consider an indicator random variable here. So I didn't want to start this slide with just talking about indicator functions in general. I wanted to get more to the point. But you may or may not have seen an indicator function in your past, and if you have, it may or may not have involved randomness. If I define this function I'm about to define using random variables, the indicator itself becomes a random variable. What do I mean? I'm going to use a capital I for indicator. You can use many symbols here. You could use your favorite indicator variable notation if you've worked with them before. And I'm going to have a subscript here that shows a set where capital Xi is less than or equal to x. This is going to be a function that returns a value 1 if your randomly sampled value xi is less than or equal to x, and 0 otherwise. Now, because xi is unknown to us and a random variable yet to be observed, the value of this indicator is unknown to us and yet to be observed. So it itself is a random variable. And this is the key piece of how we're going to write down a formula for the empirical distribution function. Here it is. For a random sample, capital X1 through capital Xn, the empirical distribution function is f hat of x, capital F hat of x. I put a subscript here of an n to show the dependence of this formulation on the number of values in the sample. I didn't write that before. I could have written it before. I could leave this out now. My capital F hat of x and my capital F hat sub n of x are the same thing in this video. It's just that I'm adding the subscript now to stress the dependence on n. So we're going to define this as 1 over n times the sum as I goes from 1 to n of the indicator that capital X sub I is less than or equal to x. So I claim this is going to do it for us. Let's look at a concrete example when this is no longer random. Let's go back to our 4-point data set. If I want to compute the empirical CDF at the value, say 2.78, you already know how to do this. You would say, what is the estimated probability based on these data of seeing a value less than or equal to 2.78? You would say 3 of these values fit that bill, but 1 doesn't. So that probability would be estimated to be 3/4. But now, based on our new formula, we're going to get 1 over n, where n is 4, and we're going to get a bunch of indicators that take us through each value in this data set. So we look at the first value here. This is a realization or observation of capital X1. And you say, is this less than or equal to 2.78? Yes or no? If it's yes, and it is yes, you put in a 1. If it's no, you would put in a 0. But it's yes. And then you look at the second value and you say, is this less than or equal to 2.78? Yes or no? 1 or 0? The answer is yes, so we get another 1. If this value 0.47 is less than or equal to 2.78, that indicator is going to turn on and be 1. But the final value, 3.22, is not less than 2.78. So we get a 0 for our indicator. So you can see what these indicators have done. They've popped in some 1s and 0s and essentially counted the number of values in the data set that are less than or equal to 2.78. And we end up with 3 times the 1/4 and 3/4. So this is what's going on here with an exact example. But again, we want to look at it up here before we have the sampled values when things are still random, because there's nothing random going on down in my example. But before you take this sample, before you generate it and you don't know what's coming out, you don't know what the CDF is going to look like. And that's where the randomness and true fun comes in. Okay, so again, what we're trying to figure out is if the random sample truly comes from a distribution with CDF F, and we compute the empirical distribution function, we want to look at whether or not it's close enough in some sense that we are going to define to the underlying CDF F. So we want to know how this behaves as a random variable. So let's break it down. Let's look at these terms first. Note that the indicator that capital Xi is less than or equal to x is a random variable, right? Because until I've observed capital Xi, I don't know whether this is going to be 1 or 0. And in particular, note that it's a Bernoulli random variable because it does just take on the values 1 and 0. The Bernoulli random variable has a parameter, and it's usually denoted by a lowercase p. And p would be the probability that this Bernoulli random variable takes on the value 1. So the probability that this indicator is equal to 1. But this indicator is equal to 1 if and only if the event down here being indicated happens. So this event that the indicator is 1 is equivalent to saying that capital X sub I was less than or equal to x. And this probability is precisely the underlying CDF f of x. That is the CDF for x1, x2, for capital X1, capital X2, and all of these random variables we're working with. So we have a Bernoulli random variable with p equals f of x. Now, this x, in everything we're looking at for the moment, you can think of as a fixed real number. We do eventually need to talk about looking at all of the x's on the real line to compare the true CDF and the empirical CDF, but for the moment, we're looking at one fixed x, which means this is just a number, and it's a probability between 0 and 1, and it is the p for our Bernoulli distribution. So I want to look at now the distribution of not just a single indicator, but the entire empirical CDF, which looked like this. This 1 over n is going to make things just a little bit tricky, not too bad, but I want to get rid of it for the moment and move this to the other side so that we're just looking at a sum of indicators or indicator random variables. And as you know, the sum of Bernoulli random variables, if they're IID, that sum has a binomial distribution. And the first parameter is the number of Bernoullis you're adding together. And the second parameter is that success probability, that probability of seeing a 1 in the Bernoulli distribution, the little p, which we said was capital F of x. As a reminder, and this is totally a parenthetical statement, not to be confused with any other x's in this lecture, but if x has a binomial distribution with parameters n and p, then we know that the expected value of x is n times p, and the variance of x is n times p times 1 minus p. So I want to use this on this fact right here. We now know that the expected value of n times the empirical CDF is this n times this f of x. And so if you want to get down to the expected value of the empirical CDF itself at this fixed x, you can just pull this n out front and divide it to the other side. And it's easy to see that the expected value of the empirical CDF at any fixed little x is equal to the true CDF at any fixed little x. So that bodes well for this being a good estimator of the true CDF. We talked about maybe how much it changes between samples. Let's look at the variability. First, let's look at the variance of this random variable here. Because it's a binomial random variable, we know how to compute this. We're going to get n p 1 minus p, but p is capital F of x. So we're going to get n capital F of x, 1 minus capital F of x. And again, if we want to hone in on this empirical CDF here alone, let's pull out this n. Constants pull out our variances squared. So we'll get an n squared in front. And when you divide that to the other side, we'll get a little bit of cancellation, but we'll be stuck with one n remaining in the denominator. The variance of the empirical CDF at some fixed x is capital F of x, 1 minus capital F of x, all divided by n. This is kind of a nice result because capital F of x is a CDF evaluated at a real number, and a CDF is a probability. So f of x is always between 0 and 1, so nothing gets too crazy in this numerator or unbounded, but you can see that because of the denominator being n, as your sample size gets large, this variance gets small. And yet the expected value of the empirical CDF is the true CDF, at least when we look at it pointwise like this, at any one particular real number x. So on average, it's right, and the amount of variability we see around the true CDF at that point is shrinking to 0 as your sample size gets large. The next thing I'm going to say, if you don't know what I'm talking about, please do not worry about it. You don't need this to go on in this course. But if you've seen or had mathematical statistics or something like that, then the 1 over n times the sum of the indicators that we have for our empirical CDF, if you redefine that indicator random variable or rename it and call it y sub I, so let y sub I be the indicator that x sub I is less than or equal to x. Then the empirical CDF that we wrote, 1 over n times the sum of the indicators, is 1 over n times the sum of some y's. This is the sample mean of the y's, y bar. And you may recall from some probability or statistics course, the weak law of large numbers. A sample mean under a condition of having a finite variance for IID random variables, a sample mean converges to the true underlying mean of the distribution, which in this case, the yi's, those indicator random variables, each have expected value capital F of x. What I'm trying to say is, we know if you've had the right background courses, then you may know that the empirical CDF at this point x is converging in probability to capital F of x. This is just another way to say that the empirical CDF is getting close to the true CDF and that this is a good estimator for the true CDF. So this result is the weak law of large numbers. And if you don't know what I'm talking about, don't worry about it at all. You're not going to need this information going forward. This is, however, a convergence for a single point x. And if we want to compare the empirical CDF to the underlying CDF, we kind of want to incorporate all x's somehow. So we're getting there. I'd like to take a moment to look at another example of a true CDF versus an empirical CDF. So let's go back to that exponential distribution. If you have an exponential distribution with rate lambda, the PDF for that distribution is lambda e to the minus lambda x for x greater than 0. And if you need the CDF, The capital F of x is the probability that the exponential is less than or equal to x. And you can get that by integrating the PDF from, in general, minus infinity up to x. But because the exponential does not take on negative values, I'd be integrating the PDF is 0 in a whole lot of places. So I'm going to go from 0 up to x. And you get 1 minus e to the minus lambda x. And if you sketch that graph, it's going to look like this. Now, all CDFs have to either equal or be going to 0 as x goes off to negative infinity. I haven't drawn the CDF over here, but it should be 0 over here because the exponential random variable only takes on positive values. And all CDFs either equal or go towards 1 as x goes to infinity, and that's the kind of behavior we're seeing here. So if I knew how to randomly sample from the exponential distribution and produce, say, 4 values, an empirical CDF might look something like this. With another 4 values, the steps might actually end up above the CDF. It's going to look different every time. We've talked about how this thing is random and based on the sample that you simulate. But I did want to look at what happens when n gets larger. We've talked a little bit about a kind of convergence. If you are sampling correctly from this exponential distribution via your simulation algorithm and you let n get large, you're going to see something more like this, hopefully, kind of a tight fit of this step function around the true CDF. These two functions look close yet again using an eyeball test, but the question once again is, are they close in a more formal sense? There's many ways to measure the closeness or the distance between these functions. Don't get on me about the formal definition of a metric. I'm just saying distance, sort of colloquially. But one way to measure it is to use the Kolmogorov-Smirnov statistic, which is defined as, it's usually denoted by a capital D sub n, and it's defined to be the maximum distance between the true CDF and empirical CDF, where this maximum is taken over all possible points between minus infinity to infinity. So we're looking at the entire x-axis and how far the empirical CDF differs from the true CDF. The question again is, are they close? And that translates to, is this D sub n small enough? If you were to compute it for your sample and get a small number, the question is it small enough? I feel a hypothesis test coming on. We are going to reject the idea that the sampled or simulated values are coming from the target distribution with an underlying CDF F if this number is too large. And the hypothesis test that is coming in the next video is going to tell us what too large means. How small does this need to be for us to be comfortable saying we did the right thing? Can we get a so-called critical value that if D sub n surpasses that value, we're going to say, no, these are too far, my simulation is wrong. We're going to talk about all that and more in the next one, so I hope to see you there.